Hello, Finance 217. I'm here. I'm going to go over, as promised, quiz 2. Now, this would be the dog quiz from fall 2016, quiz number 2 that covers modules 4 through 5B. I'm only going to go over the one quiz. I'm not going to go over both quizzes. Both quizzes are pretty similar. I'm going to walk through how to answer all three parts. I'm going to do that now. So the first part of quiz 2 involves a contingency table, which looks like this. And there are basically 5 questions that you have to answer. I ask them and you answer them. And we are doing the same stuff we were doing with the pivot tables or developing contingency tables, except in this case, we have counts. And whenever we calculate a probability, we always need frequency over total sample. But the total sample, might change from time to time depending on what we're looking at. For example, the part of the question that says, of all leashed dogs, implies that we're not going to be dividing by 37. Because in this case, we observed 37 different dogs, but not all of them were on leashes. Only 14 of the dogs that we observed were on leashes. So when we answer these questions and it says of all the leashed dogs or of all the big dogs, we have to remember what it is that we're taking from our base. This is the same data that was just presented there. Oh, shoot, except it doesn't say total. I need to put totals on here. And you know, it would make sense to do like a bunch of addition and stuff, but hey, here's a little bonus learning Excel style. Alt equals, hold Alt, hit equals, and that gets you auto sum. But that's pretty lame. Control Z, undo. I'm going to hold Shift, highlight all those, and then do Alt equals. That way I can do auto sum of all those at the same time. And I'm going to do that again for these 3, Alt equals, and now I have the same number. That's pretty cool. Anyway, Alt equals is great. Question A. Real estate. A. Question A says, what's the probability that someone had a tiny dog? So in all of these cases, we're going to need a frequency and a total sample. There's a number of different ways that we can go about answering these questions. This is the logic that I'm going to use. I'm going to cut it up and divide it up, and there's a bunch of different other probability rules. But when looking at a table like this, here's a very straightforward way to go about it. We're looking for someone who had a tiny dog. Well, there are 7 tiny dogs on leashes, 11 tiny dogs with no leash, for a total of 18 tiny dogs. The total number of dogs is the total number of dogs. So 18 divided by 27 gets me a probability of 0.486. And I want to, no, you know what? That's too many decimal places. Let's shrink it all the way back down. And I believe the quiz says, round your answers to 2 decimal places. So round your answers to 2 decimal places, 0.49. There we go. So question 1, 0.49. B. What's the probability that someone had a big dog with no leash? So we're still going to be basing this out of all dogs, all 37. So we want not I8, we want the total number of dogs, 37. But a big dog, well, there are 4 big dogs, but big dog with no leash, there was only 1 big dog with no leash. 1 big dog with no leash out of 37 total dogs means E11 minus F11, or about 3%, 0.03. There's 1 big dog with no leash out of 37 total. See? Someone had a tiny dog or a dog not on a leash. Here's where we start having to think about ors versus ands. So when we just looked at a question that says big dog with no leash, sure, there were 4 big dogs and there may be 23 dogs without leash, but there's only one big dog with no leash. So when we talk about a big dog with no leash, we got to one dog. In this case, a tiny dog, there are 18 tiny dogs. Dogs not on a leash is 23. So we say 18 dogs. Well, we should probably use parentheses. No, we don't, because we're going to do this at the end. Good. So we do 18 tiny dogs plus 23 dogs no leash, 41 dogs out of a total of 37 dogs. And then when we say, let's just go ahead and say 41 divided by 37 means the probability of finding a tiny dog or a dog not on a leash is 1.11. It is bad news because probability cannot be, well, it has to be less than or equal to 1. That number is too big. Well, why is it too big? Well, first off, if we look at the dogs with no leash, there's 23, and the tiny dogs here means that we have this little orange overlap of 11 dogs who are both tiny and no leash. We should not be counting them twice. There are effectively 37 dogs that we're looking at. And if you highlight none of the column or row headers and you just look at the total number of dogs, down here we get, again, in our status bar, it says sum of 37. There are a total of 37 dogs. And if we only look at this, and this, those are the 5 cells which contain dogs that we should be counting. We actually get a sum of 30. So we should be looking at 30 out of 37, not 41 out of 37. In fact, the way we do this probabilistically speaking is we take the column sum, which is 18, plus the row sum, which is 23, and then you subtract the overlap so that you don't count them twice. 18 is 7 plus 11. 23 is 11 plus 2 plus 1 plus 9. Notice that when we added 18 and 23, we would have counted 11 twice. We only want to count it once. And now, that's an answer I'm more comfortable with, 0.81. Of all the leashed dogs, what's the probability that someone had a big dog? Well, of all the leashed dogs means that our sample should come from, and let me get rid of the paint. Thank you for your patience. Of all of the, go back to the question, of all the leashed dogs, so those are the ones I'm concerned about. Of all the leashed dogs, of which there were 14, what's the probability someone had a big dog? And we say that there were a total of 4 big dogs. Therefore, copy this down, 4 out of 14. Well, in fact, that number again is wrong. That number is wrong because this number 4 includes big dogs that were on leash and big dogs that were not on leash. And we should not be including these because those aren't on a leash. The question specified, of all the leashed dogs. So as soon as we say of all the leashed dogs, we don't care about anything else. We only care about the leashed dogs, of which there were 14. And of those 14, 3 were big, 0.21. Last but not least is E. Of all the big dogs, what's the probability someone had a dog that was not on a leash? So again, we're only looking at big dogs. And there are 4 big dogs. Of all the big dogs, that someone had a dog not on a leash. 3 were on a leash, 1 was not on a leash. There we go. Those are the answers to the first section. They're just probability questions. Probability questions are mostly questions that we have to worry about. What is the base out of how many? And the big thing is don't double count things. Like we saw when we were looking at tiny dogs with no leash. Don't double count things. Lucky for me, I noticed the probability greater than 1, and that was indicating to me that something was wrong. But if that probability had not been greater than 1, I may not have noticed that something was wrong. Make sure you don't double count. And almost habitually, I want to ask if there's any questions, but there's no one here to ask them. Question number 2. The probability of someone wearing earbuds is 0.3. You look at 10 people. Round your answers to 2 places. So I presume that there are a number of questions here which pertain to that. Now, if I can find my binomial probability simulator, and here we go, this looks very similar to the probability distributions that you'll be given for your particular quiz or for your test. If you are unfamiliar with those, go to the statistical tables module in Sakai, and you will see that there is a binomial probability table for n equals 9 to n equals 11. And the one we need is n equals 10. We know we're going to need n equals 10 because right off the bat, our question says we are going to look at 10 people. That means my number of trials is 10, n equals 10. So this is the table that I need, n equals 10. Also, the probability that someone is wearing earbuds is 0.3. So my probability of success, no matter if it's no one, everyone, at least one, more than one, fewer than one, my probability of success that someone is wearing earbuds is 0.3. If everyone is wearing earbuds, that's 10 successes. If no one is wearing earbuds, that's 10 failures. No one is 10 failures or 0 successes. Everyone is 10 successes or 0 failures. Because this 0.3 is my probability of success. I'm going to look at all of these bits. No one, everyone, at least one, more than 5, fewer than 5. I'm going to look at all of those as a number of successes, which, if we look at our binomial probability table, the numbers 0, 1, 2, 3, 4, 5, all the way to 10 are listed here. Because if you try 10 times, you can succeed up to 10 times, but you cannot succeed 11 times, and you cannot succeed fewer than 0. It's possible that you fail every time. It's not likely that you fail every time, but it's possible. There's a 3% chance that you fail every time. And once I've selected n equals 10 and that the probability of success is 0.3, this is the only column I need, which I believe if you've got access to this document, I can, yeah, sweet, I can now do that. That's the only column that I need, is the column right there for n equals 10 and 0.3. All the other numbers on the sheet are pretty irrelevant to you, except for these. I mean, for now, they're irrelevant, and the relevancy will change. Here, for me, because there's going to be arithmetic involved, I would prefer just to set my probability of success in here, 3, with the number of trials is 10. Now we can see that we've got the same numbers. Again, there's that 3% chance of 0 successes. That these are all the numbers I need. Now I'm going to use my status bar down here to calculate sums, but I will highlight things as the question requires. There you are, quiz. Question 1, the probability that no one is wearing earbuds. Probability that no one is wearing earbuds is associated with 0 successes. 0 successes means 0.0282. Or if we're rounding our answer to 2 decimal places, well, why don't we just do that? About 3% or 0.03. A, 0.03. Make sure I'm not using any of that. All right, cool. A is 0.03. I don't like that. How about this? Yeah, I don't like that, but it prevents me from having a couple of dots next to each other. Let's put them over there too. Cool. B, everyone is wearing earbuds. How many is everyone? When we're talking about 10 people, every one of 10 is 10 successes. Well, if there's a 30% chance someone is wearing earbuds, I don't think it's likely that everyone is going to be wearing earbuds. Talk to 10 people, all 10 wearing earbuds? I don't think it's going to happen. If we were to take this out further, we'd see that that's not exactly 0. It is tenths, hundreds, thousands, 10,000s, 100,000s, 6 millionths of a chance. So if you were to observe 10 people 1,000,000 times, 6 times you would observe everyone wearing earbuds. It's a weird way to talk about that, but that's what we're saying, is that 6 out of 1,000,000 times you will be able to find groups of 10 people, all of whom are wearing earbuds, if the probability of success is 0.3. Did I just break it? A little bit. See, at least one person is wearing earbuds. Well, if one person is wearing earbuds, then one person is wearing earbuds, then at least one person is wearing earbuds. If 2 persons is wearing earbuds, then at least one person is wearing earbuds. If 3 people wearing earbuds, at least one person is wearing earbuds. If 4 people is wearing earbuds, that means at least one person. What's this mean? Well, in a probability distribution, the sum of all these probabilities here, that demonstrates all possible outcomes that we can have. And the sum of those probabilities is 1. And I just wonder if that can turn into a cool, like this. I guess it's everybody. This is all possibilities, all 11 possibilities. Right here, that's our 3%. That's the probability of no one wearing earbuds. That's the probability of one person wearing earbuds, 2, 3, 4. Everything except for this little blue wedge right here. If I remove that, can I? No, that's as far as I can get you. Okay. That's as far as I can remove that thing. But let's just fill it with something like that. I think it's poop. So if I get rid of that one and I have the rest of these, that's everything else. That could be 1, 2, 3, 4, or all 10 people. That's 6 1,000,000ths. Well, if all 10 people are wearing earbuds, that's at least 1. This answer is, and well, let's just do this right. Uh-oh. Well, that's not good. There we go. By the way, that's just using a couple bits of Excel. The ampersand does concatenate. It combines a string, which is how I previewed the answer, rounding the sum of those things. I just took this chart and added up all those proportions there. There's a far easier way to do this, and this is the way I recommend that you do it on your test or your quiz, would be to say, rather than adding those things up, just give me 1 minus whatever that value is. Because if no one is wearing earbuds, then at least one person is not wearing earbuds. However, for all other random variables x, at least one person is wearing earbuds. If I know the sum of all these is 100%, and I simply remove that one, I blew up everything. Bring it back. Not all of them. Again, just removing that 3% leaves me the complement, or 97% there. That's at least one person is wearing earbuds. More than 5 people wearing earbuds, I'm not going to mess around with that pi again. I just want to make the distinction between what more than 5 and fewer than 5 is. So more than 5 would include 6, 7, 8, 9, and 10, because all of those are more than 5. 43201, 43210, minus 1, if you're a Vandals fan. All of those are less than 0. Or sorry, less than 5. These are all more than 5. This is not the complement of this. The green and the orange are not complements. They would only be complements if 5 was assigned to one of them. But more than 5 does not include 5. Fewer than 5 does not include 5. If these questions had said 5 or more, well, I would include 5, because while 5 is not more than 5, 5 is 5. 5 or more would include 5. 5 or more would include 5. But we're not including 5 because the question is more than 5. But once we've identified what our random variable x is, all we have to do to get to the end of these questions is a bit of arithmetic. And make sure your fingers aren't as fat as mine. And remember to follow rounding instructions. And remember to tell it how many digits to round to. Some of those in my status bar says 5% or 0.05. I'm going to do the same thing down here. Maybe I can get it right the first time. Probably not, because that's not how these things go. Space in the thing. We're going to round something to decimal places. Notice you add these two together, 0.05 and 0.85, you get 0.9, which is 10% short of everything, because we've left out the probability associated with x equals 5. So the biggest thing to remember when it comes to binomial probability experiments is the random variable x is a number of successes. So first define what success means, whether it's flipping a coin and landing on heads, whether it's pulling a numbered ball out of a sack, whether it's seeing a certain number of dogs on leashes, or whatever it is. In this case, what are we even looking at here? The context is wearing earbuds. The context becomes so irrelevant to me that it's just about, well, if n is 10 and pi is 0.3, let's start chopping it up. And that's the way I look at these problems. And again, that's why I always try to pull out the essential information. But the essential information in this problem, n equals 10, pi is 0.3. Identify those two pieces, and then the questions all just vary on x. The third question that we have to answer here is a continuous probability question. Continuous probability question says the number of students at a PC field hockey match is normally distributed. On average, there are 50 fans at a game with a standard deviation of 8 fans. What is the probability that 64 fans are at the game? All right, so I'm going to try to draw pictures here because I could show you the Excel thing, and maybe I will show you my Excel tool for that. But for now, I still want to be able to put us in a position where I can draw pictures. So the 3 essential pieces of information that we get out of this, oh, this is so bad. I should be using PowerPoint at this point. We know that the distribution is normal. We know that the average number of people at the field hockey game is 50. So mu equals 50. And we know that the standard deviation is 8. 8 or 6? 8. Now I'm using the conventions of mu and sigma here. Had there been information that it was sample level information, that I took a sample of all the games from a particular season, I may have gone with X bar and S. But given that there was no sample specified, I'm simply working with those are the pieces of essential information that I have, and I'm going to treat them at the population level. Now I want to illustrate this thing which I have just described, so I'm going to draw a except for this little bit over here, it's not a bad normal distribution. I've drawn a normal distribution because this tells me that I have a normal distribution, which I'm now going to illustrate with the pieces of information I have available over here. One of the pieces of information that I have is that the, oh yeah, raw scores are in green, that the mean of this distribution is 50. And I know that the z-scores, well, the z-score for the mean is always 0. It doesn't matter if it's a normal distribution or if it's a uniform distribution. The shape of the distribution doesn't matter. The z-score for the mean is always 0 because that's what its formula is. This is a raw score of people that's at 50. This is exactly what the scenario told me was the case. Now, there are a certain number of steps that I'm going to follow in order to answer this question, but let's see what we're going to be asked first. It looks like the first thing we're going to do is we're going to take a raw score of 64 fans and convert it to a z-score. The second step is we're going to convert that z-score into some sort of probability. And then we're going to answer the question, what's the probability that there will be more than 64 fans? So in no case here are we actually starting with the probability proportion or percent and moving to a raw score. The only thing we're going to be doing is going from raw scores to, nice arrow, to z-score. Oh, no, stop it. To z-scores. That's... All right, calm down, Jeffrey. To a z-score. Oh, that's even worse. Can I just get a pen back? To a z-score. We convert a raw score to a z-score. And then we're going to convert a z-score to an area using our table, area. And then we're going to convert that area to a proportion, probability, or percent, because that's what the last part of the question for parts B and parts C both say. We're asking, what is the probability? The thing that follows what, in this case, the word probability, is our destination. And we're going to start with whatever information we have. In this case, we have 64 fans is what's given to us. So if we start with 64 fans, our first question is, what's the z-score? In order to calculate the z-score, I am going to go back to Excel and say that the z-score equals x minus mu over sigma, where x is 64, mu is 50, and sigma is 8. Therefore, my z-score equals x minus mu over sigma. Z-score is 1.75. My z-score is 1.75. Part A answered. Z is 1. Oh, wait, shoot, I don't have my pen anymore. At 1.75. 1 down, 2 to go. Now we're going to come up with the probability of attendance between 50 and 64. And that's this piece in here. As it turns out, it happens to be the same as the area that we're going to look up in the we're going to look up in the table. But for part C, which is going to be the answer over here, we're going to have to do a little bit of subtraction. Whereas the thing we come up with here, same as the area we look up in our table. I say that because the area we look up in our table has that particular shape. Notice that this shape and this shape here, boom, that shape looks the same as that. With the center at the 0, oh no, we're getting crazy, centered at 0. So having a z-score of 1.75, I work from the outside where the z-scores live, whether it's on the table or in the picture. Oops, well, technically speaking, that is on the outside. Whether I'm on the outside here or the outside of my table, I have z-scores on the outside. Now this is the area associated, 0.4554 is the area associated with 1.70. You can think about it like these are dollars and dimes, and these are pennies. And what I'm after right now is a z-score of $1.75. Don't think about it like dollars and cents. It's just the 2-digit convention. The same way it would be weird if someone said they owed you $2.7. No one does that. No one owes someone 70 cents either, but $2.70 is the way you would owe someone $2.7. For us, we have 1.7, 0, 1, 2, 3, 4, 5, 1.75. So we follow the 0.05 column down to the row, which is the same as 1.7. Therefore, an area of 0.4599 is the answer to B. If we round this, let's follow rounding instructions if you don't mind. Round to 4 decimals. Hey, we're going to leave this as 0.4599. Part C is the probability that there are more than 64 fans. Well, we just did between 50 and 64. And because in a normal distribution, it's not all the time, but in a normal distribution, the mean and the median are the same. 50% of stuff is on one side, and 50% of stuff is on the other side. This is 50%. Because it's the 50th percentile. It's the 50th percentile because of this. Not this, but because of this. The median is above 50% of stuff. This is above 96% of stuff. That is 96% of stuff. Therefore, 64 fans is the 96th percentile. But the answer C, all we have to do is take this 50% here, that's above the median, and we're going to subtract this bit here, which we just looked up in the table. And let's go ahead and say 0.5000, which is half everything above the median, minus that value we looked up in the table, 0.0401. And that's 0401. And that, folks, is the answer to part C. And that, folks, is the dog quiz. Now, there's another quiz. I can't remember if it has something to do with dogs or not. But whatever that quiz is, it's the other one. You follow more or less the same steps to get there. We've got a contingency table, binomial probability experiment, and continuous probability experiment. That's the quiz. So students that are taking it on Monday, good luck. Students taking it on Tuesday, also good luck. And I'll see you around.